Kirwan, it's called the Kirwan surjectivity result, which says that so if you look at the inclusion of the zero level set of the moment map, and you form so in general, in symplectic geometry, we like the case where G acts freely on the moment level set, so that we can take the quotient, or maybe it acts with some finite stabilizers, and you can get a quotient symplectic orbifold. But irrespective of whether the action has finite stabilizers or not, Kirwan proved that if you restrict from the equivariant cohomology to the cohomology of this zero level set, then that map is always a surjection. And so you can use this. So the motivation here is that oftentimes this quotient is some kind of moduli space that's presented, if it comes from algebraic geometry, is presented as a GIT quotient. So for example, in her thesis, this is her thesis, she was thinking about the moduli of n points on the projective line up to rescale. And she, in this open, in algebraic geometry, this quotient is kind of, you think of it as eliminating the sort of the bad parts, so you can form a nice quotient space. It's called the GIT quotient, and this gave her sort of a procedure for calculating these two theorems. Like the first theorem tells you how to calculate the Betti numbers of the equivariant cohomology, and the second theorem at least tells you that there's a surjection. You'll see that from the proof you get more information about this cohomology. So those are the theorems that I'm trying to.
Do you want only zero, or it also works for other value of the moment map?
Well, you can shift the moment map if there is a shift of the moment map. Then if you can shift, you need it. You need to preserve this equivariance condition, because so I should say G, when I say equivariant, it means that G acts by conjugation by the adjoint action.
So the first theorem means it looks like a product.
Yeah.
The fibration.
Yeah.
The second theorem, you said, well, what does it mean? The intuitive meaning of the second theorem.
Well, yeah. In the homotopical term, that's what I'm going to answer for you.
Okay.
Surjection is maybe not such a natural thing from homotopy point of view. So that's maybe part of what I'm going to speak about. So let's say you're looking at the abelian case. I want to sort of, so both of these theorems are proven using Morse theory in some sense. So that you have two different Morse functions that you want to consider to prove the two theorems. They kind of come from the same argument applied to two different Morse functions. So in the first case, we're kind of looking at the following construction. So you're considering primarily the abelian case. To get something about the non-abelian case, you would just kind of look at a maximal torus. And then for any sort of element of your Lie algebra, you can consider this function, which is you just pair your moment map with this element of the Lie algebra, and you get what's called like the beta component of the moment map. So that's a function, and it's an old theorem of Atiyah that's actually always a Morse Bott function, and the critical set will be sort of, so if you have sort of an irrational element of your Lie algebra, it won't quite generate it. It will generate a subtorus by taking the closure of that one parameter family, and it'll be the critical set will always be the fixed locus. So if you choose kind of a generic element in there, a generic enough element, your critical set will actually be the fixed set of your whole torus action. Using this theorem a bit, Atiyah sort of gave a structure theorem for what the actual image of the moment map looks like. So what you have is that the fixed point sets, they all map to some single points, and then the image of the moment map in Rn is kind of the convex hull of those points, which are called the weights of the action. And so the equivariant formality will be looking at these kind of Moore-Spot functions. To get the surjectivity result, you're looking at a slightly different Morse function or Morse type function. So you sort of choose an invariant inner product on your Lie algebra, invariant under the adjoint action, and you look at the norm squared as a function to R. And then you can sort of just figure out what it means to be critical in that case. But the critical sets are a little bit more delicate to describe. They're sort of, what you do is, so in the abelian case again, you maybe seeing a picture is best, but you have sort of any of these sub hyperplanes or generated by the weights, so sort of faces of your moment polytope, and you're looking at the points that are sort of closest to your zero, where you place zero. And over that, there'll be some sort of critical set that lies there. So maybe a picture would be more instructive. So you'll have something like this. If this is your moment polytope for P2, standard moment polytope, then so for each of these sub-convex hulls of the sub things, hyperplanes generated by the weights, you have some point on there that's closest to what you've chosen to be the zero level set, and your critical sets sort of lie over there in some way. They're not, in this case, they're not necessarily manifolds, so this function is a little bit worse behaved. It's not actually a Moore-Spot function in the strict sense. It's some Moore-Spot Kirwan function. So part of the thing she had to prove was that you could still, the constructions, like the Morse inequalities still apply to this mu squared function. But here's the theorem. So you can still, what you get for all these, you have these critical sets indexed kind of by points in your Lie algebra, and you get a stratification given by the gradient flow. And what you had to prove is sort of that still makes sense, even though you don't have Morse or Moore-Spot singularities. But you still get, just from like the usual Morse inequalities, you get a spectral sequence associated to this Morse function, and the result that she proved is that spectral sequence actually collapses. So that's sort of the more fine statement I was mentioning. And going back to here, so one of the strata is always, when you have mu squared, zero will always be a critical, your inverse image of zero will always be a critical set of that. And then you have all these other critical sets. But that's sort of somehow, in your spectral sequence, the fact that it collapses, it gives you a filtration of the cohomology, whose lowest piece is that cohomology of the lowest stratum in your Morse filtration, which is the zero level set. And so that'll tell you that once you quotiented out all the other stuff, you've got something surjective. So that's how she proved her theorem. So why, what's the mechanism? Like if you do this, what's the sort of mystery here? Well, so you have to somehow use equivariance. So let's say you're looking at a very simple example of just P1 or S2 with sort of its standard moment function. And you're looking at mu squared, so somehow you would have three critical sets. And if you're doing things non-equivariantly, then clearly, if you look at the Moore-Spot spectral sequence associated to this this function, it wouldn't degenerate. It won't calculate the cohomology of S2, but if you do things equivariantly, it does. So what's the sort of mechanism here? And the idea goes back to Atiyah and Bott. So there's a criterion, which is that, so these strata, you have some smooth stratification, and you have equivariant Euler classes associated to each of these, the normal bundles of the strata of your stratum sitting inside of M, and as long as that's not a zero divisor in the cohomology of the stratum, then the stratum is equivariantly perfect. So so how does that work? So if you look at the so that you kind of using the Tom isomorphism, you get some kind of long exact sequence you imagine adding on a stratum one at a time, and you're considering the Tom, by the Tom isomorphism, the relative cohomology of this adding on that additional stratum gets identified with the shifted cohomology of that stratum, and you want to kind of show that that basically this map here is injective. So you're kind of just adding on the cohomology of each stratum one at a time, and so you can if you take this. So if you show that want to show this is injective, then you compose it with the restriction back to the stratum. So you have the Tom isomorphism and then restricting back to the stratum, and as long as and that composition is going to be your multiplication by your equivariant Euler class. So as long as that map is injective, so the Euler class is not a zero divisor, then you get that the connecting map is indeed injective, and or maybe better to say the connecting maps are zero. So your long exact sequence splits into a bunch of short exact sequences. So that's really what you have to prove, is that in each of these cases, so we're going to, for these Morse functions, that Euler class, equivariant Euler class is non-zero, or not a zero divisor.
D beta is the dimension of the stratum.
What?
D beta is the
yeah. The dimension of the codimension of the stratum, I think.
N minus D beta is the dimension, or D beta is the dimension?
D beta is the dimension, yeah. Okay.
So I'm confused about this example.
Yeah.
You're having North Pole, South Pole, and equator being this S beta.
Yeah.
And then what's the Euler? See, for the Euler class to exist, you have to have a complex. And this is normal bundle is just line bundle for that.
Oh.
Line bundle for the equator.
Oh yeah. The normal bundles. So which normal bundle to what?
So the equator, right?
Not the equator. No. The stratum. So the normal bundle here would be, that's the full manifold. So here, you'd have normal bundles to these, but those would be.
Because I wasn't sure whether equator is also included.
Okay. So, right. So here's the sort of key lemma is due to Atiyah and Bott in a very. I mean, they kind of did. The history is that Atiyah and Bott were studying the moduli of holomorphic vector bundles on Riemann surfaces, and they kind of came up with this argument, and then Kirwan sort of systematized it to all quotients. But this is sort of the historical origin. And what so you imagine, so you have a space, an equivariant complex vector bundle over some space, and you want to assume that there's a circle in there that fixes exactly the zero section. So it acts non-trivially on the fiber-wise, but the circle acts, you know, trivially on the space, but non-trivially in the fibers. The fixed locus is exactly the zero section. And then in that case, the equivariant Euler class is not a zero divisor. So why is that so? Well, because rationally if you have a non-abelian group, the cohomology of the G equivariant cohomology embeds into the T equivariant cohomology. And then you can kind of imagine you take your torus and you split it as you have your distinguished S1 and some complementary torus, and you can write the cohomology as being just the cohomology of the classifying space of BS1 tensored with this equivariant cohomology of the remaining subtorus, and then so if you your Euler class over a point like this, the hypothesis says that if you're just looking at the representation of at the tangent space of any point, you have some non-trivial kind of zeroth order term to your Euler class, and then you have plus sort of terms of positive degree. But then if you filter by the degree here, then the action will just be, the only term you'll see will be this sort of lowest order term, which in this case, you know, you can pretty clearly see it just kind of acts on this part non-trivially, and there's no sort of torsion anywhere, so that it's a you know, the associated graded action is clearly injective, and so that means the actual action is injective. So, yeah.
Fixed point set being the zero section. I mean, this S1 actually fixes the whole Y.
Yeah, the S1 fixes the Y, but then in the fiber it's doing something. We're assuming the representation is non-trivial in the fiber-wise, and that's sort of the. Yeah, exactly. So, so that's sort of the key thing, and then you know, in both cases you have to do some. In the case of that we're looking at you know, in the case of equivariant formality, where you're looking at just this kind of you know, your fixed point set, your critical sets are really just the fixed sets of the circle action, then of the torus action, excuse me. Then if you take kind of a generic enough circle inside of your torus, that will have this property. It'll act by zero it'll act trivially on the fixed set, but by definition, but it'll act with non-trivial weights on the fibers. So that's the easy case where you can easily see that there's a circle in the you know, part of the Kirwan surjectivities, you know, involves a more detailed analysis of the strata to produce a circle. It's called in GIT language, it's called the Hilbert-Mumford circle, Hilbert-Mumford subgroup. So you can sort of see that this argument fails over integers, at least for Kirwan surjectivity, and the reason is that that the leading order term, you know, this alpha 0. So if you had some torsion, for example, in this other piece of the cohomology, or maybe it's better to think about if you were working mod p. If you're working mod p and your sort of weights are all kind of suitably divisible by p, then that leading order term will just kind of identically vanish mod p, and so you wouldn't be able to prove the surjectivity, and indeed it doesn't work. It doesn't hold because there's a very simple example you can write down which says basically if you look at C cross C with the diagonal, well, with the product action of S1 times S1, then the quotient will just be kind of a product of the, we'll make it act by, weight 2 to make it interesting. And then if you look at the quotient as a, equivariantly, it has the homotopy type of a product of classifying spaces of Z mod 2Z, and then by the, if you just work out the Kunith formula, you'll see that there's some odd degree two-torsion cohomology that appears, and so you can't, whereas the cohomology of the equivariant cohomology of your ambient space is all concentrated in even degrees, so you couldn't have a surjective map integrally. Although, any other prime mod 3, it's fine, and so forth. So we want to try to understand this, but on the flip side, actually, Atiyah and Bott and also Kirwan, they sort of observed in their original papers that in the cases they were interested in, where the quotient was smooth, that you did have an integral Kirwan surjectivity. The Kirwan restriction was integrally, the map was integrally surjective. So we wanted to try to understand why that might be the case. So let's, somehow if you're thinking about in terms of homotopy theory a little bit, this, we sort of notice that the key to whether the argument works or not has to do with how the, the first, sort of the leading order term of the first Chern class behaves in, just in the cohomology of BS1, which should kind of, maybe if you're a little bit familiar with some homotopy theory, reminds you of the formal groups. So there's just a general class where you can make sense of these, where the cohomology of BS1 has exactly the same sort of structure over the cohomology of a point, and where the Chern classes are sort of easy to calculate. And that's called the complex orientable theory. So if you just a general definition that as long as you can just start with this very simple definition that something is complex orientable if when you restrict to the cohomology of, you take CP infinity, your BS1, and you restrict to S2, that's surjective. And just from that definition, some standard kind of arguments say that if you then choose something some explicit representative that surjects, you get isomorphisms of the cohomology of BS1, a product of BS1s with the kind of graded power series ring over your coefficient ring. And just sort of all the usual theory of Chern classes that in Stasheff, Milner style stuff generalizes to this setting, and you have Chern classes valued for complex vector bundles. Just universal theory sort of works. So this is the sort of setting that we consider, and maybe we can ask. So it works. The Kirwan surjectivity argument works rationally. What other cohomology theories does it work for? So just to sort of say a little bit more about what I just said. So if the way to, what you really want to look at is if you have a tensor product of line bundles in this cohomology theory, how does it, so I'm thinking of what's relevant to the case of this, what we said, the Kirwan surjectivity argument is taking powers of a line bundle. So, but there's, for any of these cohomology theories, you formally just have, you identify the cohomology of BS1 squared in terms of this graded power series ring, and you get something called the formal group associated to the complex oriented theory, and it satisfies certain properties just coming from the fact that if you tensor line bundles, tensoring of line bundles, commutative, and so forth. And so you get this formal group. And we want to ask, can we run the argument in different formal groups? So in cohomology, you have the standard formal group. In complex K theory, you have what's called the multiplicative group law. This V1 variable, don't worry about what it means too much for the moment. It's kind of like a periodic variable. And complex cobordism, that's sort of the universal theory. Those are probably the main complex-oriented theories that people encounter in a course in algebraic topology. But complex cobordism is kind of the early theorem of Quillen proved that it's like the universal complex-oriented theory. So if you have so you get sort of choosing complex orientations gives you multiplicative natural transformations from your complex cobordism theory to whatever your complex-oriented theory is. But not, this is where the connection maybe to Dennis that I was mentioning in a little bit vague connection, but I'll go with it, which is that, from those are sort of the geometrically defined complex-oriented theories, and the remaining ones are sort of, well, at least now constructed using purely algebraic techniques in homotopy theory, which were pioneered by Dennis and then taken up by May and other people. The one that's sort of relevant here is you can sort of is something. The first thing is called this Johnson and Wilson theory, which basically it's kind of I can't really obviously get into the technical detail, but you could write down what its coefficients, meaning what it is on a point, very very explicitly, and it turns out that under special situations, if you can write down a map of the coefficients suitably, then you can actually construct a spectrum that algebraically realizes this, whose coefficients are precisely this ring, and it's a spectrum, it's a complex-oriented theory, and so forth. And so the complex cobordism is a very infinite. It's natural in that you can describe the cycles very very nicely, but it's very infinite. And so what you're basically doing here is quotienting out by a bunch of generators to get something finite. And sort of the number of variables you have is something called the height. And that's sort of, so we're going to be working with things of some height. And from there, you can do all kinds of stuff. So you can complete it so there was this ideal that arose, which was just all the variables v0 through up to say like these variables here are periodic, so they you have a graded. If you go up to Vn minus 1, you kind of have a kind of ideal you can complete at, and that would be one choice of so-called Morava E theory. And then you can also quotient by that ideal and get coefficients which have a graded field. So you're just left with these variables, which sort of basically is a field from a graded point of view. And then there's some other, instead of quotienting out by p, modding out here, you've modded out by p, which is v0. That was something maybe I didn't mention explicitly. If you mod out by p to the r, you get some sort of thickening of this Morava theory. And these are sort of the main players in what I want to say. But you don't have to know that much, at least to begin with. What do you even know about cohomology anyways? You know the axioms it satisfies and what the coefficients are, more or less, and then you use that to do your computation. So how these spectra are actually constructed, you can kind of at your own risk, forget about it. You just treat them like, okay, these are my coefficients. Everything is sort of built formally. It satisfies all of the cohomological axioms.
Where does the P arise in the Morava-K theory?
What?
What's the P in the Morava-K theory?
Oh yeah. So yeah. Maybe I should have made that more explicit. I took, again, yeah, the connection to Dennis. I localized. So I at P. So when you do, we're going to look, homotopy theory is always a good idea to start by localizing. And this, if you're just sort of willing to accept it, it's actually a really nice cohomology theory in that it's, Morava-K theory, it's one of the, you can prove that Morava-K theory and usual Eilenberg-MacLane cohomology at fields are the only cohomology theories that satisfy a Kuhneth formula. So
compact CW complex.
what? Finite? Yeah, finite CW complex. Yeah. Otherwise, you got some kind of completion thing that happens. And this is sort of the key thing, which is I was talking about the Chern number. So what you're really looking at is what is the Chern class of the universal bundle over BS1, and you want to know what's actually the Chern class of the pth power of that. Well, if you worked mod p, you would get, the group law would tell you would get 0. I mean, you just get nothing. But if you work in this Morava-K theory, this is some invertible element, and you're multiplying by some u to some power times an invertible element. So this is much better from our point of view in terms of this Atiyah Bott argument, because it's it's not 0. That's the main thing that's relevant actually. And finally, there's another really nice thing which is very related to this actually. So if you think about, if you do usual cohomology, and if I get far enough, this will be very relevant. If I have a finite abelian group, and I'm looking at the ordinary cohomology of that, that's kind of a mess because it has an infinite number of an infinite number of not generators, but it's concentrated in infinitely many degrees. So it's definitely not a finite thing, but this Morava theory is finite rank, and it's very much related to this calculation, because basically, when you want to calculate the cohomology of if you use a kind of a Giesen sequence, what you're basically going to be doing is taking the cohomology of BS1 and quotienting out by this for, say, like a P group, like Z mod PZ. And so for Z mod PZ, you'll exactly get that the rank is P to the n minus 1 over the coefficients. So the point is that if you use this better behaved Morava cohomology theory, then Atiyah Bott lemma just works in the Morava theory. And as a consequence, this you get a surjective, and in fact the whole Morava spectral sequence that you get degenerates in this for the equivariant cohomology. But
Working over Z?
This argument would work over, for any of the Morava theories that I mentioned. So not over Z, but we're going to use this to get information about the ordinary cohomology.
P it works.
Yeah. E can be any of the cohomology theories here. So it could be this thing which is maybe over p-adic integers, and the first one is a completion, or over f, basically over fp coefficients. But the important point is that these Morava K theories, they actually give you, if you take the height large enough, they actually give you information about the ordinary cohomology by the Atiyah-Hirzebruch sequence. Because if you basically, if we think about the Atiyah-Hirzebruch sequence associated to this, this is a finite dimensional space. So as long as we take the height to be very big, the cohomology, the Atiyah-Hirzebruch sequence has a very high periodicity. And so, sort of as long as the height is large enough for any finite dimensional space, the Atiyah-Hirzebruch sequence degenerates. And so that tells you that this cohomology map, if all of those maps are surjective, the only way that could be the case, as long as the height, as long as you have any, this were true for any sufficiently large height, bigger than the dimension, basically, something like that, then this map is also surjective. So that's how you can use these strange cohomology theories to get information about the one, classical one that Eilenberg-MacLean thing that you care about. So the result is that that as long as you have a free action, which means that the cohomology, the quotient, is actually a finite dimensional space. So that's where we can apply our, that's where we can really hope to get information about that map. Then we have surjections modulo every p to the r in cohomology, and as a consequence, we get that the Kirwan map is split. So that gives a conceptual explanation for what Atiyah, Bott, and Kirwan observed in their example calculations. That it works integrally because in those cases we were looking at a smooth quotient. And more generally, if you have finite stabilizers, then as we saw in our example, the model example of just C cross C, the theorem doesn't work. But as long as you invert all of the orders of the stabilizers, the different stabilizers along mu inverse of 0, then again you have a surjection, and you get something that's additively split. So
does that sentence mean the orders of all stabilizers, each divide L? What is that?
So you choose. So you take the GC, the greatest common multiple of all the stabilizers.
Tell me what the English means.
Okay, the order of all stabilizers. So
Each stabilizer.
Each stabilizer.
Divides L.
Yes.
What's the key property of the Chern classes that you use to prove the statement from our okay?
Oh, it was just the fact that it was just the fact that it's really non-zero mod, at every, so these are kind of primes, and just that the restriction when you go to this prime is non-zero, that's enough to prove it. Really what you use is that it's some power, strictly speaking, what you're using is that this is invertible. And then, this part is very easy to understand its action on the associated graded. So you have like something that just multiplies by u times something invertible, which definitely doesn't, like this action is definitely injective, and then this one will be injective. So that'll be the nature of the calculation. So, okay. So, so I said about what happens with formality. Okay, so here it's sort of a similar, so you have to sort of invert, so if you have a torus action, then the proof, everything that I just outlined, you look at this generic component of the moment map, you run the same argument, and for a torus, you can prove that that you have this, that the cohomology, the equivariant cohomology really behaves like a product vibration. And if you have a non-abelian group, then it turns out that there's, you have to kind of remove, there's a kind of a universal obstruction, which is the fact that if you're looking at just the case of, so you choose some maximal torus, and then, and so you have this cohomology of BG embeds into the cohomology of, well, it maps to the cohomology of BT. But if you think about the fiber of this map, this is kind of a, in itself a Borel space. So you're looking at the cohomology of G acting by, like say for SO3, by translations on G mod T. And that can be made, at least like in a semi-simple case, made Hamiltonian. So, if the formality were to hold, this map should be injective. But we know there's plenty of cases where, say, this cohomology has torsion. Say for SO3 in H3, this has torsion, and this has no torsion. So this map cannot be injective. But if you invert those torsion primes, so this is called the reduced torsion index, which is just the product of all the torsion primes in this cohomology, then you do in fact get, this map becomes injective, and then we can prove that the result holds there. So that's the general theorem. If you kind of eliminate obvious obstructions, then the result holds for general G. So this was all kind of a meditation. Well, thinking about, I said there's a connection to Stony Brook, and that hasn't been so clearly revealed yet. So all of these results were sort of, maybe I should, there's some, you can actually make this fancier in some way. You can do it in spectra. You can do it for any complex oriented theory, but I'll skip over that part maybe for time. And instead, I want to talk about why this sort of came about, and why I chose to speak about it here, related to work of Mark and also other Stony Brook people who may not be here now. But basically, there's a whole quantum a more powerful approach to these kind of problems using quantum cohomology that maybe should be better known. And the starting point goes back to a construction of Seidel. So if you have, more generally, instead of having a circle action, you can consider a base loop of Hamiltonian diffeomorphisms. And using that loop, you can form sort of a fibration over CP1 by just kind of gluing along that loop of diffeomorphisms along along the boundary. We're kind of going to identify X by its action under this loop of diffeomorphisms. And this is a symplectic, if you start with you have your symplectic manifold, this is a symplectic construction. So in other words, the fiber bundle can be made symplectic. And you have these two fibers that are sort of diffeomorphic, or under this thing, symplectomorphic to your original symplectic manifold. And so if you have it's a natural thing to do whenever you have a symplectic fibration is to count over CP1, is to think about counting holomorphic sections, sort of that map. You have two mark points, and we're going to map one to the fiber at 0 and one to the fiber at infinity. And you can kind of define an operation on the cohomology that's, or maybe it's really quantum cohomology for those that are familiar. So you kind of have a parameter that measures, roughly speaking, the area of your section class. And you get something called the Seidel operator from the cohomology tensor, some Novikov ring, to the cohomology tensor, that Novikov ring. And this Seidel operator, the sort of why it's a very interesting thing is because it's actually an invertible operator. So what is that? Let's think about what that means. So why is that the case? Here's kind of the picture proof of that. due to Seidel. So you imagine sort of taking, you can build a space where, it's a fibration over the one pointed blow up of P2. So it fibers over P1 with fiber P1. And then so you have this B, it maps, in particular, you have this blow up and then it maps to P1. And the fiber over a generic fiber will just be like a product of X cross S2. And then over like some central fiber where you've blown up basically, this X cross S2 degenerates to a copy of your your Seidel spaces over given by phi, your loop of diffeomorphisms, and its inverse. And so if you think about this, counting holomorphic curves in these fibers, it's kind of invariant, the count of holomorphic curves. And so you just kind of degenerate everything to this limiting fibration. And that limiting fibration is going to be basically a union of the two of the Seidel space and its inverse, and basically that tells you that if you kind of compose the Seidel operations for phi and its inverse, that gives you the same thing as the Seidel operation for the trivial fibration, which better be the identity map. So the Seidel operator, the outcome is the Seidel operator for the inverse loop will be the inverse of the Seidel operations. And that's a very powerful statement because if we take it immediately gives you something quite interesting, which is that if we take the loop, you have this loop of Hamiltonian diffeomorphisms, and you have just the inclusion of your homology as, say, the fiber over 0, then that map has to be injective because this Seidel operator, it's given by counting some Gromov-Witten invariants that take place in here. And that count, you have to have at least a non-trivial count in order to make the composition of to make the Seidel operator invertible. You better have a non-trivial count for every homology class. And so there'll be some non-zero Gromov-Witten invariant, which is really an invariant in here. So the image had better be injective. And if you think about what that means that the cohomology of, just by some standard Leray spectral sequence arguments, that tells you that the cohomology of this P phi with Q coefficients has to be isomorphic to the cohomology of M tensor over Q with the cohomology of S2. That's just, if you play with the Leray spectral sequence a bit, you get that very easily. And then, so McDuff and Lalonde, who was a student here, they proved that they generalized this to any Hamiltonian, so any bundle whose structure group is Hamiltonian now over any projective space, CPN. They proved this kind of formality. So in particular, Kirwan's result, we're looking at things over the formality for a torus. You can truncate, basically you could prove it because this cohomology is finite dimensional, it has finite degrees. So you can prove it over a sufficiently large, it's easy to see you can prove it over a sufficiently large dimension projective space, and so this result is a much stronger.
So this means the structure group of the bundle is
Hamiltonian.
Hamiltonian to diffeomorphism.
Yeah.
That's all that works.
That's all that means. Yeah. But it applies much more generally because if you have a family of algebraic varieties, projective varieties over CPN, that's also going to have a Hamiltonian structure group. So in the case of a algebraic family over CPN, a projective family, you get from this, you also kind of generalize some cases, or of Deligne's formality for cohomology in projective families. So
analogous theorem in algebraic geometry.
Yeah, the analogous. What is the analogous theorem? So I'll take B to B, so P to B. So let's say the coefficient system is, so pi 1 of B is the identity. Then the cohomology, so this is
Your algebraic varieties.
yeah, B is a projective smooth algebraic variety. P is also a projective smooth algebraic variety. Then the cohomology of P, with Q coefficients again, is going to be the cohomology of M tensor with the cohomology of B.
So the map has no singularities.
Yeah, it's smooth fibration. This has to be a fiber bundle, yeah.
And that goes back to what name?
Delene would be the one.
Okay, fine.
Yeah.
So remember,
Yeah.
55 years ago.
So you know, this perspective has really become really powerful lately due to work of Mark and Abu Zayed and Smith, because, so like traditionally Gromov-Witten invariants, like these Seidel operators are defined with Q coefficients because, you know, your moduli spaces are orbifolds. They have sort of, and we know that the fundamental cycles are, you know, in an orbifold you can define it with Q coefficients, but not so well with over Z. But going back here, actually, this is sort of maybe a shadow of the key idea. We had this calculation, elementary calculation here. Where is that elementary thingy? Oh yeah, here, this one. That if you have a finite abelian group, the Morava theories are finite. So, and they do, there's kind of like a version of Poincare duality that holds for finite groups, Morava K theory of finite groups. And that can be souped up into Poincare duality for Morava K theory. And that allows you basically to define Gromov-Witten classes in that plus some other good understanding of the moduli spaces allows you to define Morava classes. And using that idea, the same idea basically is, well, you have to, again, there's some additional steps that you can prove that if you're in the same setting, the cohomology with any complex-oriented coefficients it kind of behaves as a product. It's formal. This is for any sort of Seidel space fibration. And maybe it's better to call it a proposition, but we kind of generalized with Shaoyun Bai, we generalized this to the result about CPN. So this gives you a different way to make the argument about Kirwan formality in complex-oriented cohomology theories.
P is like CP1.
P phi is this total space of the fibration over CP1.
You use the limit as the transition function of the equator.
Yeah. And so in particular, if you have an algebraic family, I don't know, you know, how motivated people are, but this kind of over CPN, this kind of formality Delene kind of formality holds in any complex-oriented theory. But that's a very specific kind of family. But we can maybe, I don't know how many minutes, I maybe have 1 minute, so I'll say this is a lot to say in 1 minute. But basically, there's a different perspective on how to deal with orbifold stabilizers due to Bai and Xu. And Fukaya, actually, the idea was given by Fukaya, and using Mark's work, Bai and Xu were actually able to realize it, to not get Morava invariants keeping the orbifold stabilizers, but to try to instead kind of discard them suitably. So just get invariants of the free part of the moduli space. And this is called again, as I say, F and O are Fukaya and Ono. There's also Parker. This is a kind of a new construction. But using this, instead we were able to prove that maybe a more interesting, this works in a more interesting class, a more general class of varieties. So if you have something which we call it stably rational, so if your base times a, basically you can think of rational, that would be already sufficient. So if you have a rational base, meaning you're just birational to CPN, then you have formality for families with any coefficient field, not just over Q. So this generalizes this Deligne statement, but for specific bases, the formality holds integrally. We don't know about, for technical reasons, we don't know about other complex theories, if that's interesting. But yeah, that's a good place to stop. So thank you.
Why did you say it's a generalization of Deligne? He doesn't assume anything.
I didn't say general. I said for these bases, we get, for these bases, for these specific, for bases of this form, this, this class of bases, it's not generalization. It's a different, we use coefficients which are, prime characteristic field, or even integral. You can even get this over integers. For these bases, it works over integers. K is a field of prime characteristic.
Okay, fine. So
it's not generalization. It's a
partial extension.
Yeah, it's a
Okay.
Oh, it doesn't work integrally. Deligne's theorem does not hold integrally. You can basically you can take this example, and you can approximate this space by an algebraic space, and this vibration by kind of algebraic spaces, and you can cook up an example of varieties where Deligne's theorem fails integrally. So there's those bases that you get from here are not stably rational. That's kind of the conclusion.
You made the statement that Lalonde was a student here. That's completely false. He was a student at Alsace in Paris, and before that at Montreal, where he spent most of his career.
Okay.
He worked with Dusa McDuff a lot, so.
Yeah, maybe I had
He was a student here, not technically.
He was no, he was never at Stony Brook.
No.
Okay, sorry about that then. But, well, sorry about that then. Yes.
We would have been glad to have.
Good to know.
We have other questions for them.
What's the technical difficulty when you try to prove that last theorem for any complex-oriented cohomology?
Well, the way we proved this is a bit different than some of the other things. So the way that we prove the question was why are we not able to do this theorem with any complex-oriented cohomology theory, whereas the other results were for complex-oriented cohomologies? And the reason is because the argument. So if you have something that's rational, say, that means you have some kind of roof diagram between, like say CPN and whatever your base actually is. Where this is a blow up, and this is actually a strict birational map. So for this part, like if we the way that we prove the theorem is we say, okay, there's a line here that avoids the blow up locus, because the blow up locus is complex codimension 2, and that gives me a non-vanishing Gromov-Witten invariant upstairs here as well. And basically, if I look at the fiber, so I have some Gromov-Witten invariant, and in the fiber over that curve will be the sidal space of that curve, and that will be that'll give me some non-vanishing Gromov-Witten invariant in the sidal space over this blow up. But that only kind of proves injectivity of the fibers. It's not strong enough to prove the splitting in complex-oriented theories. It's just a kind of a different. The proof has a different nature than the other proofs, basically. So, it's kind of some kind of result. The thing we prove is some kind of result about relating Gromov-Witten invariants of sidal spaces to bases.
main question. What are the kind of miracles that make this all this stuff happen? Like one is kind of this original thing was maybe almost Bott's thesis, where it shows the Morse function on the loop space of the Lie group as complex cell decomposition. Sort of incredible, miracle out of the blue. And
Yeah.
that's a perfect Morse function. That's where this word perfect came from. So
Yes.
there's a lot of perfectness in here.
Yeah.
It's one kind of miracle, somehow getting these perfect things. What else is?
Well, the other thing is this.
Key, Morava-K theories or something.
Well, Morava-K, yeah. Well, yeah. So one. Yeah, there's a lot of different random things
What?
there. A lot of random concepts.
No. What is the miracle? I mean,
Yeah. So one miracle would be for Morava.
Cleverness and all that.
Yeah. So one miracle would be the fact that I would go back to here. Really, what's the form of the group law for Morava-K theory? So like this computation that this is at least finite abelian groups, but you could there's some version of this kind of reducing for finite groups that you get something finite dimensional. That tells you that that you can get. I mean, that's basically the heart of Poincare duality in Morava-K theory. And then at the same time, the group law here.
What's your definition of a Morava-K motion?
Okay, so
I mean, to make this true.
okay, well, so any of these,
Oh,
just this list. That's how I was thinking of it here. But if you're a fancy homotopy theorist like yourself, you would say Kn local, any spectrum in the Kn local category, that will work. So if you have to build this Morava-K theory, and then you localize there, then I guess that's maybe another Dennis construction, but maybe I don't know. Anyway, the point is, like any of those, it would hold. So these are kind of the most common examples one would consider. And those are the miracle. Yeah, those are the main miracles. And the other thing would be this invertibility of the Seidel map, which comes from this fiber. Those may be like the takeaways for grad students or other people. So this construction here of this vibration that goes back to Seidel, which gives you the fact that the Seidel map is actually invertible.
Where do you actually use the Kunet isomorphism for?
What?
The Kunet isomorphism for Morava-K theory. Where do you actually use it?
Oh, where I didn't use that. I just think it's it's just an illustration that all I was trying to say with that is that like if you're willing to digest the definition of Morava-K theory, it's like it's maybe as good as Eilenberg-MacLean, in some ways better behaved, but like you know its coefficients. It has this. You can prove this nice. Coefficients are graded fields, so that's kind of what underlies this statement here. And it's the only, maybe other than Eilenberg-MacLean fields, it's kind of the only set of cohomology theories that have the Kunith property. So maybe I just feel like as a geometer, someone who's a geometer, they might say, I don't know what a cycle is in this theory. I'm gonna be afraid of it. But if you accept this algebraic construction, I think maybe in fact you gave a construction of like Morava-K theory geometrically. I don't know that so well, but maybe there is a geometric way to think of it as Bordisms with some certain kinds of singularities. But Dennis would know much more than me. But anyways, if you're a geometer, you might think I'm not going to use this, but it's actually a nice thing. So.
If you get any more questions, there's a tea break upstairs. Continue. Let's thanks. Is this the limit?